right. So let me continue with the same topic. Again, I will solve one or two problems in checking whether a decomposition is a lossy decomposition or lossless decomposition. And then finally, we'll study the topic checking whether a dependency is preserved in decomposition, right? So these are the two topics that you need to be familiar at the end of the day. So let me share you the problem. Right. So yesterday, I think we tried solving a second and third problem. Right. Third problem we got some wrong solution, and I think today Subramaniam has given us the correct answer. So let us try working with the first problem. Right. So example 3, first subdivision. So you have a relation with attributes A, B, C, D, E, F, G, H, I, J, which is fragmented into 5 relations: R1 with attributes A, B, C, R2 with attributes A, D, E, R3 with attributes B, F, R4 with attributes F, G, H, and R5 with attributes D, I, J, right? So again, there exists some functional dependency between the different set of attributes in this relation. A, B determines C, B determines F, D determines I, J, A determines D, E, F determines D, G, H, right? So now you are expected to check whether the subdivision 1 is going to be a lossy decomposition or lossless decomposition, right? So anyway, let me share you the solution. So the union of the fragmented relations A, B, C, union A, D, E. So you get A, B, C, D, E, F, G, H, I, J, right? So the union of the fragmented relations give you back the original relation. So condition 1 is satisfied, right? So now we are going to look for condition 2. So ABC intersection AD is going to be A. A closure is going to be ADE, right? So A closure is going to be ADE, which is a super key of R2, right? So we are going to combine the relations, combine the fragmented relations ABC and ADE, right? So R12 denotes ABCDE. Now again, you are going to find the intersection between R12 and R3. So ABCDE intersection BF, it gives you B. B closure is going to be BFGH, or B closure is going to be BF, which is going to be the super key of R3, right? So B closure is going to be BFGH, which is going to be the super key of R3. So you are going to combine the relations R12 and R3, right? So you have R13, a relation with the attributes A, B, C, D, E, F, right? So now you are going to find the intersection between A, B, C, D, E, F and relation R4, F, G, H. So again, the intersection value is going to be F. F closure is going to be F logically determines GH. So F closure is going to be FGH, which is the super key of relation R4, right? So now you are going to combine the relation R4 with relation 1, 2, 3. So it's going to be A, B, C, D, F, sorry, A, B, C, D, E, G, H. So finally, you are going to find the intersection between R1, 2, 3, 4 and R5. So A, B, C, D, E, G, H intersection D, I, J, you get D. So D closure is going to be D, I, J, which is a super key of R5. So we conclude that the decomposition is a lossless decomposition, right? So you can make a note of it and check whether whatever we have done is correct. So the decomposition of subdivision 1 is going to be a lossless joint decomposition, right?
Sir, can you scroll it down to the next page, sir, once? Yes, sir. R123 we have A B C D E F, and then we intersect it with F G H again. So shouldn't R1234 be A B C D E F G H?
Yeah, it should be A, B, C, D, E, F, G, H, right?
Yes, so in the end, we are missing F in our 1, 2, 3, 4, 5 as well.
Right. I think now it's correct, right?
Yes, sir. Even in last
So
relation,
down
yeah,
to, yeah.
yeah, yes, sir. Now it's
Final answer. Yes, sir.
A, B, C, D, E, F, G, H, I, J, right? Right. Is it correct?
yes, sir.
Yes.
Right. Right. So now I have some problems for you, some tutorial problems which you can solve and answer, and you can share the screens or you can display the results. Right. I think, but it's quite simple. I think I have taken it from some websites. So consider a schema or with attributes x, y, z, w, and functional dependencies that exists on the relation or x determines y and z determines w. So you need to identify whether the decomposition of the relation schema or into relation x, y, and relation zw is a lossy or
It's
lossless.
lossy.
It's a lossy decomposition because
The
Intersection is
intersection
yeah,
conditions is
intersection is
condition.
not.
second condition is not met, right? So R1 intersection is null. So the second condition is not met. R1 intersection R2 is null. So it's a lossy decomposition. Right. So the question two is like you have a relation schema with five attributes or with five attributes x, y, z, w, p. It is decomposed into two relations, R1 and R2. I think the same thing is repeated, right? So it's again a lossy decomposition because the intersection is going to be null. Let us look into the question three. So you have a relation schema R with attributes x, y, z, w, p. It is decomposed into two relations, R1 with attributes x, y, z, w, and R2 with attributes w, p. So you can work on question three. So the first condition is met, right? So union of the fragmented schema, it gives you back the original schema, and the intersection values also it's going to be not null, right? X, Y, Z, R1 intersection R2, the intersection value is going to be W, which is not null. Now you need to check whether W can determine any one of this relation R1 or R2. So W cannot determine either the relation R2 or R1. So it's going to be a lossy decomposition, right?
Yes, sir.
Yes.
Uh, so that condition is not met in this case. And the last question have a relation x, a relation R with attributes x, y, z, w, p, which is decomposed into fragments x, y, z, w, and the other fragment is going to be x, z, w, p, right? So the union of the fragmented relations gives you the original relation. So the condition one is met. Condition 2 is also you can meet it, right? So x, y, z, w, R1 intersection R2, you get ZW, right? So
X also,
ZW,
sir.
yeah, X is a W. So X can determine Y, Z can determine W, right? So it's a lossless decomposition. It can determine all the elements in the relation. So it's going to be a lossless joint decomposition. At the end of the session, I will upload this Word document into your course materials folder. You can have a look into it, right? So hope now you are familiar with checking whether a decomposition is a lossy decomposition or lossless joint decomposition. So let me move on to the next topic. So I hope the problem is visible, right? So
Yes, sir.
Yes, sir.
document is about checking whether the dependency is preserved in a decomposition, right? So there are two properties of decomposition. So the decomposition should be a lossless decomposition. And the second condition is that the dependency among the attributes in a relation should be preserved in a decomposition, right? So the algorithm input is like X determines Y in functional dependency, and the decomposition of R into fragments R1, R2 till Rn. So it returns true if X determines Y is in G closure, that is Y is a subset of Z, else it returns false, right? So here you need to know this formula. Z union, Z intersection Ri closure intersection Ri, right? So let me try to solve this problem. Let me show you this problem, and I will try to check whether uh, you know how to check whether dependency is preserved in a decomposition. So consider a relation R with attributes A, B, C, D, E, F, right? So it has the following functional dependencies. A determines B, C, D, A determines E, F, right? B, C determines A, D, B, C determines E, B, C determines F, and so on. And it is decomposed into three fragments: A, B, C, D, B, F, and D, E. Now we need to check whether the dependency is preserved in a decomposition or not, right? So you are going to project the dependencies into the decomposed schema, right? So you have three fragments of relations: A, B, C, D, B, F, D, E, right? So the following dependencies can be projected into the following decomposition, right? So the first dependency, functional dependency, can be projected into the first fragmented relation. A determines B, C, D. Similarly, B, C determines A, D can be proved, right? Similarly, in the fragment B of B determines F can be proved, and D determines E can be proved, right? So the only thing you need to check is like you need to check whether A determines EF, right? Since the functional dependency is spread across multiple fragmented relation, you need to prove whether A determines EF is true, BC determines EF, BC determines E is true, BC determines F is true, right? That's it, right? So you need to check whether only these three functional dependencies are preserved in the decomposition or not, right? So we have made an assumption that whenever the dependency exists within the same fragment, we assume that it can be easily proved that the functional dependency is preserved in a relation. So we are concerned only with checking whether BC determines E is true. The functional dependency BC determines F is true, and A determines EF is true, right? So for that we are going to use this formula, right? So initially the left hand side is stored in the attribute, stored in the variable Z. So Z is equal to BC. So we are going to use this formula to calculate whether BC determines E is true. Z intersection Ri, Z intersection Ri closure, Z intersection Ri closure intersection Ri, Z intersection Ri closure intersection Ri union Z, right? So first you are going to take the first relation. So BC, let Z be stored in the temporary variable, let BC be stored in the temporary variable Z. We are going to find Z intersection R1, then Z intersection R1 closure, Z intersection R1 closure intersection R1, and finally Z intersection R1 closure intersection R1 union Z, right? So this is the formula for checking and updating the value of Z, right? So initially let us check for BC intersection R1. So BC intersection R1 is going to be BC. Z intersection R1 closure, BC closure is going to be BC determines AD, BC determines EF, right? So BC closure is going to be all the elements in the relation, right? Then you have Z intersection R1 closure intersection R1 is going to be ABCD, right? And then you are going to update Z value. So Z intersection R1 closure intersection R1 union Z. So union is at ABCD, union BC is going to be ABCD, right? So the updated value of Z is going to be ABCD, right? So the right hand side does not contain E or F. So BC determines E or BC determines F is not proved. So let us repeat the procedure. Now again Z is equal to ABCD. Z intersection R2 is going to be ABCD intersection BF. Z intersection R2 closure is going to be B closure. So B closure is going to be BF, right? So Z intersection R2 closure intersection R2 is going to be BF intersection BF, which is going to be BF. And Z intersection R2 closure intersection R2 union Z is going to be ABCD, ABCD union BF. So ABCDF, you get the attributes ABCDF. So you can prove that BC determines E is part of this. So we have proved BC determines F. Again, the right hand side does not contain E. So again, we are going to continue with the new value of updated value of Z, ABCDF, Z intersection R3, Z intersection R3 closure, Z intersection R3 closure intersection R3, Z intersection R3 closure intersection R3 union Z. You get the values ABCDEF. So we say that BC determines E is preserved. So the dependency is preserved. So till now we have proved that BC determines E is proved and BC determines F is proved, right? Now you are going to take the next dependency, A determines EF. So you are going to store A in the variable Z. Again, you are going to find Z intersection R1, Z intersection R1 closure, Z intersection R1 closure intersection R1, Z intersection R1 closure intersection R1 union Z. right? You get A, B, C, D. So you are going to again update the value of Z. Now again, you are going to work with R2 relation. Z intersection R2, Z intersection R2 closure, Z intersection R2 closure, intersection R2, Z intersection R2 closure, intersection R2 union Z, right? You get A, B, C, D, F, A, B, C, D, F, right? So A determines F can be proved. However, A determines E is still to be proved. So again, you are going to continue with that iteration. So the old value of A, B, C, D, the new value of Z is going to be A, B, C, D, F. You are going to work with the third relation, Z intersection R3, Z intersection R3 closure, Z intersection R3 closure, intersection R3, and finally Z intersection R3 closure, intersection R3, union Z, right? You get A, B, C, D, E, F, so that you will be able to prove that A determines F is also present in that fragmented relation, and we say that the dependency is preserved in the decomposition, right? So you need to find Z intersection Ri, Z intersection Ri closure, Z intersection Ri closure, intersection Ri, then Z intersection Ri closure, intersection Ri union Z, and to check each and every iteration, you need to check whether the functional dependency is preserved in the decomposed relation, right? So I'm not sure whether you are able to follow it. We'll have one more class, right? So the next class will solve some problems in checking whether the functional dependency is preserved in a decomposition. Anyway, let me load both the documents in the course materials folder. You can have a look into it. So checking for functional dependency, preservation of functional dependency is also quite simple only. Only thing you need to solve some problems and make yourself familiar with that. Any questions about the segment? Right. So we'll try to solve.
No, sir, no questions.
Right. So anyway, we'll try to solve one more problem maybe in the next class and make ourselves familiar with checking for whether the functional dependency is preserved in a decomposed relation. So if a functional dependency exists in the original schema, right, the same functional dependency should be preserved in the decomposed relation, right? Right. So that's it for today's class. So thank you for your participation. So I thank Subramaniam for coming forward and solving a quite large number of problems to help us explore more about lossy and lossless joint decomposition. Thank you, Subramaniam, for your support.
Thank you, sir.
So that's it for today's class. We'll meet in the next class.
Thank you,
Thank you,
sir.
sir.
Thank you.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.